And let's begin. So an exponential function has to grow by a constant factor, which we also call it a percent rate. Because remember, at the end of the day, we're multiplying. And when you multiply, there's a few different key words that we use for multiplication. We know that factors are multiplication, and we know that percents are multiplication. So both of those would be multiplication. Those are key words. And the general form, or the standard form of an equation for an exponential function is y equals a times b to the power of x, where a is the y-intercept and b is the growth factor. So just like we looked at in the previous problem, we have the y-intercept and then the growth factor. So I want us to take a look at this graph right here. Can anyone identify the y-intercept for me?
1.
1. And then can somebody identify the next point? So if I were to make a table of this.
Is it 2/4?
2, 4, yes, but there's something in between.
1, 2.
Good, 1, 2, there you go. So the thing with exponential functions is that if you want to find the growth factor, you have to go between 2 consecutive points. So you can't skip. Otherwise, it's not going to give you the right answer, okay? So if I'm looking for the growth factor, I can pick any 2 points, but they have to be consecutive points. So all you need to do is pick 2 consecutive points. I'll choose these 2. And you can divide the second point divided by the first point to figure out what you're multiplying by. So for example, here, I would do 4 divided by 2. What's 4 divided by 2?
2.
2. So I know that the growth factor is times 2. I'm just multiplying by 2. So all I did was I just divided in order to figure out what's being multiplied. So if my growth factor is 2, b equals 2, and a is 1, can somebody write the equation for me for this graph?
Y equals 1 times 2x.
Good, 2 to the power of. Exactly. It's kind of simple, but we just have to remember how to do it. Okay, so do I have any questions so far? Because we're going to do a couple more examples, but do I have any questions so far?
Wait, how do you get the 1 and 2 again?
What does A represent?
The y-intercept,
What does B represent?
growth factor.
There you
Okay,
go.
never mind. Thank you.
You're welcome. Let's do another one. Oh, wait, no, sorry. Before we do another one, let's also talk about what makes something like word problems. If you have a word problem, how you can determine if it's linear versus exponential. So it all goes down to keywords. So in the first example, can I have a volunteer read a savings account?
A savings account accumulates no interest but receives a deposit of 500 each month.
Okay, so what keywords do we see here?
No interest.
No interest, that's important.
500 deposit each month.
500 each month. So is this adding 500 each month, or is it multiplying by 500 each month?
Adding.
Okay, so is this going to be linear or exponential?
Linear.
Linear.
Good, linear. And the reason I highlighted no interest is, do you guys know what interest is, like actually in real life?
Is it like a percent of how much money you get?
Yeah, like amount they take from you.
Yeah, well, they don't actually take, yes, so it's kind
Like
of
taxes?
You have to pay after
kind of
you
like,
make a loan or something.
yeah, Samaj, say that again.
Time it's like when you make a loan and you have to pay back the amount, and then if you don't pay the interest, it's gonna continue to grow.
Exactly. So for example, I have student loans because when you go to college, if you take out a loan to pay for your college tuition, you also have to have interest. So let's just say my loan was $10,000, which is it sounds like a lot, but trust me, that's not a lot when it comes to college. So let's say it was $10,000 loan with 4% interest. And this is kind of like I'm giving you guys like an algebra lesson, but also a life lesson right now, because this actually like happens in real life.
Life lessons with Miss Lopez.
Life lessons with Miss Lopez. So let's say I have a $10,000 loan with 4% interest, and I don't pay it back. I don't know. I got fired from my job. Please don't actually fire me from my job. And I don't have the money right now to pay it back, right? So in the first year, it's just going to be $10,000. So this is my years. This is the amount. It starts off with $10,000. Oops, this is year 1. Or year 0, technically. At the very beginning, it's $10,000. I didn't pay anything back because I didn't have any money. So after 1 year, this $10,000 gets multiplied by 4%. But 4%, what's that as a decimal?
0.04.
0.04. Yeah. 0.04. What is 10,000 times 0.04? Can you guys try that real quick?
400.
400, right? 4,000 times 0.04 is 400. But then how much, since I'm adding that to my loan, I started with $10,000, but after 1 year, I have $10,400 because I added it to what I already had. So I'm not technically multiplying by 0.04, I'm multiplying by 1.04 because that allows me to add.
That, or is like
No, now I owe even more. Now I owe $400 more than I did last year.
Oh.
So the loan grows, but my debt grows with it. Does that make sense?
Dang.
Yeah.
That's scary.
Yeah. It's a big deal. $400 is a lot, and it adds up, because then the next time around, try this. Let's say I'm still out of a job. I still haven't paid anything back yet. Now do 10,400 times 1.04.
4,160.
Try 10,400 times 1.04.
Oh. 10,816.
10,816.
Dang, that's a big jump.
Big jump, right? And it gets worse and worse the longer you put it off. So that's why interest can be good for whoever's giving me the money. So whatever bank I'm paying back is making big bucks for every year that I don't pay. So yeah, someone who loves money is out there taking it from me. So, okay, life lesson with Miss Lopez is over, but what we learned is that interest payments are definitely exponential. Okay, so anytime that you see the word interest, you know that that's going to be exponential. For number 2, is that going to be linear or exponential? The value of a house
Exponential
increases.
because it's increasing.
Increasing by what, though? Here's the most important.
1.5.
1.5%. All right, number 3. Who can read number 3? I know Tyrone wants to, but somebody else jump in for now. I want to give everyone a chance.
Sad.
Who can read?
Now you see why I
I'll
know.
read.
All right, go ahead, Perla.
The temperature increases by 4 degrees Fahrenheit every hour, 8 a.m. to 3 p.m. one day during July.
Linear.
And why?
It says every hour, and increases by 4
It
degrees
increases
Fahrenheit.
by a whole number, not like
Decimal or percent.
Right. There's no word in there that tells me I'm multiplying. This basically is just telling me it adds 4 degrees. So adding is linear.
Every
right.
240 minutes, 14% of the rat population dies. I'm sorry.
What is this, linear or exponential?
Exponential.
Good. Percent. And then finally,
Each month there are 5 fewer, what is that?
bales.
Bales of alfalfa in the barn.
Alfalfa. It's a type of vegetable.
Alfalfa in the barn.
Good. Jalen, good, guys, good.
Linear.
Linear.
So like exponentials is percents and decimals, and linears is like just whole numbers and adding.
But be careful, because what if I said let me see, like the girl is running at a rate of 5.5 miles per hour.
Linear?
Yeah, how do you know that's linear?
I don't know. I guess because you're telling me how it's not always exponential.
Wait, what did you say, Miss? Can you repeat that?
So the situation would be Leslie runs at a rate of 5.5 miles per hour.
Oh, that's something constant that keeps being like added.
Because it's the adding per hour.
Yeah, because it's adding. And remember, the word rate doesn't necessarily mean multiplying. Just because this is a decimal doesn't mean I'm multiplying. You have to actually think of the scenario. So, and also, we also know that speed, anytime you're talking about the speed of something, that's linear. That's your rate of change.
Because it's always going to increase by a certain amount.
Mm-hmm. Okay, so speed is a big key word. Speed is always slope, rate of change, linear. Okay, so this was good. Now we have to also be able to, kind of like our bell ringer, be able to see if something is exponential versus linear on a graph or a table. So here I have a table. Take a look at the values. Try to think of the pattern. Is it adding? Is it subtracting? Is it multiplying or dividing? And then we're going to choose which is our best answer. So start by just taking a look. Take about a minute.
Miss, I have a question.
Mm-hmm.
Did you see my math in the chat?
Yeah, yes, I'm confused by it.
Okay. So it says that in 240 minutes, 14% of the rat population dies.
Uh-huh.
But there's only 100% of the rat population. So does that mean after 1,750 minutes, 15 minutes, the whole rat population would die?
After 1,715 minutes? No. And do you want to get into this? Because it's actually pretty interesting.
Yes.
Okay,
Because like, wouldn't they reproduce?
let's assume that they don't reproduce. This is I actually really like this question. How do I add a page? Hold on.
Maybe the plus at the top.
I got it. Every 240 minutes, the rat population decreases by, what was it, 14%?
Yeah.
Okay. Okay. So let's pretend we have 100 rats, just to make it easy. We start out with 100 rats.
That's a lot of rats. Well, not really.
So at 0, we have 100. After 240 minutes, it goes down by 14%, right?
We have 86 rats now.
86. Because this is minus 14%. Or you can think about it as you're dividing or times 0.14. Okay. Then now you start out with 86. So the next time around, after another 240 minutes, it goes down by 14% again, but now you're taking 14% off of 86. So what's 14% of 86?
Oh,
Like
12.04.
12.04. So what's 86 minus 12.04?
73.96.
So 70, like 4 rats.
So let's call it 74, yeah. Because we got to keep things as a whole number. Then it happens again, right? Now I'm at, what's 48 times 2?
96.
96, 960 minutes. Another 14%, but now I'm taking 14% of 74. Check that out. What's that going to be?
10.36.
10.36. So it's kind of about 10 less. So now I'm
So
at
it'll be like
64.
63.64, so around 64.
64. So notice what's happening, right? So each time, yeah, it goes down by 14%, but the number you're taking that from also goes down. So that doesn't mean that all of them are going to die after, what did you say before? 17?
1,002, wait, no.
1,715.
Okay, let's do it one last time then. 960 plus another
You're at
480.
19,000 minutes, I think. I'm not sure.
After another 480 minutes, what happens here?
1,920 minutes. Okay, now. Do that.
Wait, is it 240, 360, 1,200?
What?
Did I add? Oh, I might have added 480 by accident.
Yeah.
Yeah, because you're right. But either way, what happens? 64 times 0.14?
8.96.
So I'm taking away like 9. So 64 minus 9, 55.
55. Where's she going?
So yeah, it's getting smaller and smaller, but it's not necessarily going to get all the way down to 0 that fast.
Well, that's interesting.
It is. That's the cool thing about exponential growth. And
For
this
every time, oh, you can know.
And let me just finish it off. And this graph, by the way, would look something like this. So if this is my coordinate plane, the graph would start at 100 and it would go down like that.
Wait, so miss, for every time you decrease in the population, the percent you're also decreasing goes down?
Mm-hmm.
Wow.
All right. So, okay. So now we're kind of really getting into it. Good. I love that. This was a good sidetrack. Okay. Now let's take a look at these tables. Which one of these is going to be exponential? Look at the pattern.
Would it be A?
What makes you think A?
Wait.
I think it's A because first it increases and then it just like has a downfall, and then it increases and then
Yeah, so
oh no, it just increases. Never mind.
you can kind of think about how fast things go, right? So painting A starts out slow, but then all of a sudden it goes really fast and we end up at 144. With painting B, it's kind of increasing slowly the whole time. And if you actually get down to it and look at the numbers, I see that here I'm adding 300. Here I'm adding like about 306. Here I'm adding 300 and what is that? 308.
312.
12. Yeah, 312. Right. So it's adding, pretty much adding the whole time. It changes a little bit between each addition, but it's almost adding by the same amount. Whereas in painting A,
From 750.
take your calculators and divide. What's 15,750 divided by 15,000?
1.5.
1.05.
1.05. Try the next two. What's 16,538 divided by 15,750?
1.05 and like a whole lot of numbers.
but you can pretty much round it up, right, to 1.05.
And then the next one is 1.04.
0.4-ish. Okay. So again, it's a real world scenario, so it's not going to be perfectly perfect, but pretty much the pattern is multiplying, not adding. So just like Jalen said, okay, we're adding or multiplying by the same amount. So is this going to be linear or exponential?
Wait.
For painting A.
It is going to be exponential because it's being multiplied.
Exponential because we're multiplying, whereas the other one, we're adding, so it's linear. So now let's look. Take a look at the answer choices. The value of painting A increases by a larger constant rate than painting B. First of all, are we increasing or decreasing? Let's just make sure.
We are increasing.
Increasing, good. So A might be right. Let's check out B. The value of painting A decreases at a larger constant rate. Is that going to be?
No, because we're increasing, so it's not that.
C, the value of painting A grows by a larger constant percent rate than painting B.
It might be that.
Or D, the value of painting A decays at a larger.
No.
Okay,
No, because we're not decaying, we're increasing.
right. So is painting A increasing by a percent rate or a constant rate?
Percent rate.
Right, so that's why C is our answer. What's your question,
Okay.
Perla?
I was gonna ask, this is probably obvious, but I don't remember. For a linear graph or linear function, does it always have to be increasing by like the same constant for it to be linear?
Yeah, because constant, remember, constant rate. Linear
But
means it has a constant rate.
But if it's, let's say, added, but it's not constant, would that still be linear or would that be exponential?
So in this case, for example, in this case, it's adding by like almost the same amount. Almost. It only changes by a tiny little bit. And that's kind of like how in the real world in general, anytime you have a real world problem, things in the real world just aren't always going to be perfect. So if you think about it, this will probably be like a situation where the points are kind of like this, but the general shape of this graph, even though they're not perfect, it's still linear because it's still following a linear.
Oh yeah, we learned this
path.
last year. Scattered points
Mhm.
and then like a line in the middle.
Yeah, scatter plot. Good question.
Yes.
All right. Moving right along. How about here? Can I have a volunteer read? I know, Tyrone, you love to read. I'm going to let you go.
Yay. The graph of a linear function and an exponential function is shown below. When x equals 3, the linear function and exponential function are equal. Which of these statements are true?
So everyone take a look at the statements. Let's think about it.
Wait, what do they mean x equals 3?
Okay, so when x equals 3, that's over here. When x equals 3, the linear function and the exponential function are equal. So what's happening? So what's happening? Say that again?
They intersect?
Yeah, they intersect. So basically this is saying if we just kept going, the graph technically ends, but if I just extended this a little bit and for both of them, they would basically cross somewhere over here. So later on at some point at x equals a number,
And then they would never cross after that.
3 comma n, because we don't know where that happens, but somewhere they cross again. So they cross twice. So if that helps out, go ahead and reread the questions real quick. Think about it again, and then we'll talk about it.
Wait, which one is the linear one?
What do you think?
The straight line.
There you
All
go.
right, okay.
Miss, are you gonna put a poll or are we just gonna talk
No.
about it?
We're just going to talk about it. All right. So let's go through each option. A, and just say true or false. So A, the linear function never exceeds the exponential function.
True. Wait.
False.
False. Why is that false?
Wait, what does exceed mean again?
Good question. What does exceed mean like anywhere in general?
Passive.
Like to pass?
To pass or to be, when you exceed, are you above or are you below?
Above.
Above. So this is saying the linear function is never above the exponential function.
It
But
is.
where is it above? At what point does the linear function go above?
Around
Wherever that
negative
y is.
1, 1.
So basically this whole area right here, that whole section, it's above. So we know that A is incorrect. What about B?
It is also incorrect.
Because it does.
Mhm.
Like where you drew the line is gonna exceed it after that.
Good.
Point forward is exceeding
Like
it.
at around 3, n.
Good. What about C? The linear function exceeds the exponential function for values of x that are greater than 3.
I think that one might be true.
I think it is.
So
It's
Any-
out of A or D. No, not A or D, C or D.
either C or D, yeah. So the linear function, so this is telling me that the linear function exceeds the exponential function after x equals 3. So look after x equals 3. At that point, which one's on top?
Oh, the exponential.
Exponential. Oh, so it's D.
So it's D.
I knew it was D.
The exponential function exceeds the linear function for values of x that are greater than 3.
Yeah,
lot of
the
reading.
linear
That one's
one
a-
exceeds it at -1.
Yeah, exactly. The linear one exceeds from -1 to +3. But everywhere else, it's the exponential one that wins. Everywhere else, exponential is exceeding.
Okay, I understand this one. This one was easy.
Good. Okay. So now we can get to the equations. So remember what I said before, that the general form, the standard form, and this is something that you should write down, is y equals a times b to the power of x. ABX. And what does A represent?
A is the y-intercept,
And what does B represent?
like the rate of change.
Yes, but we call it something different. Does anyone remember? There, Perla said it, the factor or the growth factor.
Oh yeah, that.
How much you're multiplying. So here's a pretty simple example. Check it out. See for yourself if you can figure out what's the y-intercept and what is the growth factor. Times 4. Good. Times 4, times 4, times 4, times 4. So therefore, my B is 4. What's the A?
Would it be 2?
2. Good. So my equation would be y equals 2 times 4 to the power of x. Pretty easy, not bad, right?
Oh yeah, because yeah.
Questions?
Oh, I have a question.
Go ahead.
So you know where the exponent x is?
Mm-hmm.
Will it always be 4 to the x, or like?
Whatever that b is, whatever the growth factor is, that goes to the power of x, yeah.
Okay.
Let's do another one. Now I have a graph. This is actually kind of exactly like the bell ringer, so let's just quickly look at it. What's the y-intercept?
Ooh, the y-intercept is 1.
1, right there. And what's the growth factor?
2.
And how do you know that?
Because the first point it goes is 1, 2, and then it goes to 2, 4, and then it goes on and on.
Right, so if I put this in a table can be more useful sometimes. This is 0, 1, 2, 4, sorry, 1, 2, 2, 4. What would 3 be? It doesn't show it, but what should it be?
8.
3, 6.
Not 8, because we're multiplying, remember?
Wait.
I said
Oh,
8.
yeah.
Yeah, Jalen said it. Jalen had it. So yeah, so the growth factor is 2. So my equation is y equals
1 times 2 to the power of x.
exactly.
Yay.
All right. Okay, here's more like what it would look like on a test. So what happens is that you can write an equation and that's fine. But remember, you can always transform graphs. So when you're transforming a graph, let's quickly review this. I actually just did this today with my algebra kids.
I think I know the
Oh
answer.
yeah, it's K up, down, to the left and right thingy, right?
Mm-hmm.
Oh, I
Okay.
remember this.
Yeah, this is a throwback. So what does each of these tell me to do? What does the first one tell me to do?
Go up,
Up. What about the second one?
Down.
The third one?
go right.
Right.
Nope.
No, go
Left.
left.
This
And
one's
then right.
left. Yeah.
Yes, opposite.
And then right. Okay. So now it's telling me if this is f of x, if the first graph is f of x, which of these would be f of x equals
A.
2x plus k?
Oh, wait. Plus k.
Oh, but if k, okay, there's a lot going on. Even I didn't read it carefully. So what is the graph of f of x equals 2 to the power of x plus k if k equals -2?
It would
A.
be going down.
It would be
Yeah,
going
so it
down
would
by
be
how
A.
many units?
2.
2.
Down 2 units, yeah.
So A.
So Jalen's been saying it for years in the chat. Yes, it would be A.
Ms. Lopez, isn't 2 to the power of x the same as 1 times 2 to the power of x?
Yes.
Okay.
So like in this example, I had y equals 1 times 2 to the power of x. I could simplify this to just 2 to the power of x.
Wait, I need to write down the k thing. I'm probably
Okay.
going to forget it.
Go ahead.
Okay, thank you.
No problem. Any questions on this one?
Nope.
Okay, here's one that doesn't have a graph, but it's the same concept. So let's think about it. Can I have a volunteer read?
What would be the y-intercept of the graph? Wait, what would be the y-intercept of the graph of the function below? F of x equals 3x minus 9.
Good. And let's get in the habit of saying not 3x, but 3 to the power of x. Because
3
otherwise,
to the power of x minus 9.
thank you. Because 3x just sounds like I'm multiplying. Okay, so I have 3 to the power of x minus 9. So what type of transformation do I know that's going to be?
We're like up, down, left, or right?
Right, up, down, left, or right. Down by how much?
9.
So the original f of x would be 3 to the power of x. And then from there, I would go down 9 units. So what would be the y-intercept of 3 to the power of x?
1.
1, because 3 to the power of x is the same thing as 1 times 3 to the power of x. So I know that this is my y-intercept. So if that's the y-intercept of the original function, what's the y-intercept when I have 3 to the power of x minus 9?
Negative. I want to say -1. But.
Can you repeat that question, Miss?
If I'm, like Tyrone said, we're moving down 9 units, right? So my
Yeah.
original function has a y-intercept of 1. But now I'm moving that function down 9 units. So what's my new y-intercept?
-8.
Oh, yeah, -8 because you're moving down.
Down by 9, exactly.
I think you would get A if you just thought it was like down.
It's basically like saying kind of like y2 minus y1 in the way, kind of. If you took the 1 because that's your y-intercept, and then you subtract because that's how many times you're going down, you would get -8.
Right. So you had to take the original y-intercept, so 1, and then you know you're going down, so 1 minus 9 would be -8.
All right.
It's a little tricky, but
Yeah, I was a little confused at first, but I got it.
now another way you could figure out the y-intercept, and here's like, if you're on beast mode when you're taking your test, you would remember this. What do you plug in to figure out the y-intercept?
The
Anytime.
Where?
On any graph in the world, any function in the world, if I need to know the y-intercept, what do I plug in?
1.
Not 1.
Huh?
What's the input?
the X.
No, but what do I plug in for x? What number?
The slope? No, not the slope.
The I forgot what it was called.
What was the y-intercept of this one?
The y-intercept was 1.
1.
Okay, what's the coordinate point?
0, 1.
Oh, so the coordinate point?
What's the coordinate, or what's the y-intercept? Oh, this one's the same. Do I have any other good graphs? No, I don't. Hold on. Let me find. Okay, what's the y-intercept of this one?
The y-intercept of this one is 0, 2.
0, 2, you said? Good.
Yeah.
What about the y-intercept of this one on the right?
-2.
0, comma, -2.
0, -2, you said?
Yeah.
Si, senora.
What about here?
0, 1.
Same
Oh,
one.
0, 1, you
Four.
said?
Yeah.
Okay. So if I need to find the y-intercept, what am I plugging in?
0.
0. For any graph in the world, any graph of any function, if you plug in 0, it's going to
Miss,
tell you
I
the
was kind
y-intercept.
of thinking about that, but not exactly the 0. But I remember when you wanted to find the x, like you had an equation with the x and the y, you would take out the x to find out the y, and for the y, you would take out the.
Right. That's the
other way,
same
you know,
thing.
you guys.
It's the same thing. It's plugging in 0. This goes for, and this is this is for exponential functions, linear functions, quadratic functions, any function in the world. Plug in 0, you get your y-intercept. So here's another way you could have figured it out. What is 3 to the power of 0?
3 to the power of 0.
0.
0.
No.
3. Wait. It would be
Try it on your calculator. What's 3 to the power of 0?
3.
Yes, Perla. It's 1.
Oh.
We learned it last year. Y'all, Janellis is the only one who remembered what Miss Lopez says in class. Anything to the power of 0 is 1. So 3 to the power of 0 is 1. So this is 1 minus 9. So f of 0 is -8. So the y-intercept is 0, -8. So that was another way to do it. Questions on this one? Any other questions on this one, I mean?
No.
All right. All right, now try it on your own. Which function best represents this graph? Think about the y-intercept, think about the growth rate, see if you can figure it out.
Wait, do we say the answer?
Think of your answer and then we'll talk about it.
Okay.
The graph is going by twos, right?
The numbers that they are highlighting are going by twos, but each box goes up by one.
Okay.
I think I know, but I'm not 100% sure. So I'm gonna check.
Take another 30 seconds. Okay, I'm gonna fill in some information. What is my y-intercept?
2.
2. So
Close.
it's 0,
Your
comma
growth
2.
is also 2.
And then I have 1, comma
Quattro.
4. Can anyone tell what's happening at the 2? You can kind of see it.
The X.
Oh yeah.
Wait, which two? Oh, the X?
Yeah.
It goes up like by 5. Like it's at 10.
By
I
2.
don't know how to explain myself, Miss. I'm sorry. My brain is not okay.
It's
Isn't
not
the
at
growth
10.
2?
It's not at 10. It's at kind of hard to tell
9.
actually. I think it's crossing the 9. Yeah,
Nin.
I think. It's kind of hard to
Yeah.
tell. So actually I'm not going to use that one because I can't really tell. Okay. This is all I really know about this graph so far. So if I were going to write this in a general equation, I would do 2 times 2 to the power of x, right? But the thing is, that doesn't match any of my answer choices, does it?
No.
And if this were going by a growth factor of 2, then what should the next number be in the pattern?
4.
It should be 4,
Wait, 8,
right?
8.
Or 8, I
Wait.
mean.
8.
But is that the case?
No.
No. So that's not really what's going on here. So we need to think of something else. So maybe instead of writing a general form, we can think of this as a transformation. What you can do is you can try plugging in. Let's say I plug in a 1. What should I get as my answer? If I plug
4.
in 1,
Four.
I should get 4, right? So let's test answer choice A. What's 3 to the power of 1?
3.
2.
So is it A?
No.
No, because I want to get 4. Now let's test B. I'm going to plug in 1. What's 1 plus 1?
2. That's 9.
So 3 to the power of 2 is 9. So is this it?
Um,
How about this one? I'm plugging in a 1. 3 to the power of 1 is,
2.
right, minus 1 is 2. So is this it?
No.
Miss, so it was a 10.
Yeah, it was 10, yeah. Well, here, when I plug in a 1, 3 to the power of 1 is 1. I mean, it's 3. And then 3 plus 1 gives me,
Yeah, because I did 2 for every one. And then for the last one, I got 10.
yeah, it is 10. Yeah. So really what this was what happened is you had y equals 3 to the power of x, and then they moved it up by 1. So originally this would have been 0, comma 1, 1, comma 3, and 2, comma 9. But then everything got moved up by 1. So that's what happened. So it was answer choice D. This one was a little bit more challenging. Does anyone have any questions?
no.
Make sure you are good to go because I don't want to hear it if you don't understand it after this. Okay. All right, end behavior, another fun thing. Quick review of this. So I look at the right side of my graph and take a look at where it's going. I look at the left side of my graph and take a look
Infinity.
at where it's going. On the right side, as x approaches infinity, so that's telling me to look on the right, where is that arrow pointing? Up, down, where's it going?
Up.
Up. And that's going to go up forever. So on the right side of my graph, that means f of x is approaching infinity. Now on the left side, where is that graph going but never going to actually reach? Where is it trying to go?
To the
The bottom one?
The left side.
trying to go to the left.
Well, it's going to the left, but as far as up versus down,
It's
what
like
is
in
it
the
trying?
middle.
It's kind of in the middle.
It's trying to follow the line.
It's trying to follow the line. That's kind of a good way to think about it. You can think about it a couple of ways, but if this is my x-axis, what this graph is doing is it's trying to get to the x-axis, but it's actually never going to reach it. It's going to get really, really close, but it's never actually going to touch it. So what we call this, whenever it looks like it's approaching, it's trying to touch the x-axis, that
Negative.
means it's approaching 0.
Oh.
It's trying to get to 0, but it won't ever do so.
So if it's negative infinity, it's going to reach 0.
As x approaches negative infinity, so as x goes to the left, so this is telling me to look on the left side. On the left side of this graph, f of x, the actual function, is trying to reach 0.
Okay, got it. But it's not going to apply for every single one, right? Just for this one.
This one, yeah. So let's take a look at the next example. So again, as x approaches infinity means to look on the right. So look at the right arrow, this one right here. Where is my function going on that end?
Down.
Down. Down towards where?
Bottom.
What do we call that?
Negative infinity.
Yeah, negative infinity. Good. But then on the left side, as x approaches negative infinity,
0.
over on the left, the function is trying to get to, but will
0.
never actually reach 0.
So sad.
Sad. Very sad. Questions on end behavior?
Let me write this down.
Good. Write it down.
Okay, I got it.
Okay. So try this one on your own now. I'll read it for you. Select the end behavior of the exponential function shown in the graph above.
Oh, this is easy.
A, the graph goes from -8 to 2 on the x-axis and 0 to 8 on the y-axis. B, as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity. C, as x approaches negative infinity, y approaches 0. As x approaches positive infinity, y approaches infinity. Or D, as x approaches 0, y approaches negative infinity. As x approaches infinity, y approaches infinity.
I think maybe I want to say D.
Let's remind ourselves what these two symbols mean.
Negative infinity. Oh,
When I tell you that x is approaching negative infinity, I'm saying look on the x-axis. On which side of the x-axis does x approach negative infinity? Say that nice and loud.
left.
Left. So this is saying look left. Look at the left side. When I say x approaches positive infinity, this is telling me to look where?
Right.
Right. Here in D, it's saying x approaches 0. There's no such thing as x approaches 0 because you can either go to the left or you could go to the right. So they're just trying to trick you on that one because this is not a thing. Okay, so just so you know, D was trying to trick you. So really we're looking between B and C. So look again, look carefully. Jalen says it's C. Do you guys agree?
Wait, let me read it. Yeah, I think it's C. I agree.
Good, it is. As x approaches negative infinity, so on the left, the graph is trying to reach 0. But on the right, the graph is trying to go up towards infinity. So good job, Jalen. Nice job.
Because it also says if like x is going to infinity, y is going to go up to infinity as well.
Exactly. All right. Finally, we have exponential growth and decay, which is basically just all the same thing, but word problems. So quick reminder for growth, you can write this down. Usually it's going to be, I guess just y equals a times 1 plus r to the power of t. Does anyone remember what r represents?
The rate.
And specifically, this is the
Rate of change.
percent growth. But we have to write it as not a percentage, but a decimal.
Decimal.
And then instead of x, they just have they have a t instead, which is just time. Because with real world problems, it's always going to be something to do with time. So who can read for us this problem?
The amount of certain radioactive substance decreases by 15% every hour. If a sample starts with 100 grams of this radioactive substance, which function represents the amount of radioactive substance left after 6 hours?
Good. And sorry, I forgot to highlight it, but A is still the same thing, which is the starting amount. Because remember, y-intercept is always your starting amount. So we used to say that A was the y-intercept, but that's the same thing as just the starting amount. So let's put it all together. Here, what is my starting amount?
100 grams.
100 grams, right? What is the rate of growth?
Wait, but it's decreasing.
Oh, but it's decreasing, right?
Yeah, so the rate of decay.
So it's actually a decay. And does anyone remember what actually is the difference between growth and decay?
Growth means it's going to get multiplied, and decay means it's going to get subtracted.
Not subtracted. What's the opposite of multiplication?
Divided.
Divided. So with my function equation, with growth, you add r. With decay, you subtract r. That's the only difference. But r is still r. R is still how much it's changing by. So here, it's 15%.
15%.
But as a decimal, what is that?
1.5.
15.
0. Say that again, Jalen?
15.
15, good. Okay, so now let's fill in everything we have. So this would be y equals 100 times 1 minus 0.15 to the power of t. And what is 1 minus 0.15?
1 minus
0.85.
Mhm. There you go. And remember earlier today when Jalen said, he was like, wait, hold up. When you multiply by a decimal, you're actually dividing. That's what's happening here. It's multiplying, but it's multiplying by a decimal. So that's telling me that whatever I'm measuring is actually being divided. So it's decreasing, not increasing. Questions on how to make that function equation?
No.
Okay, try another one. This one all on your own. I'll read it. You guys think of the correct answer. The value of a certain stock has decreased by 5% per day for the past 10 days. The initial price of the stock was $30 per share. Which equation describes the value of the share price of the stock as a function of n, the number of days elapsed during the 10-day period? Take 30 seconds to think, look through the possible answer choices, and then we'll do it together. You can send me your answer in the chat privately.
Hey, didn't we do this before?
Yep, this is from an old test, actually.
This is review.
All right, 10 more seconds. You can send me an answer if you have it. All right. First off, is this growth or is it decay?
DK.
Decay. So I'm using the decay formula. So that would be A times 1 minus R to the power of T. And let's fill in the blanks. What is my A? What's the starting value?
30.
What is my R, my rate?
5%.
5%. And what's 5% as a decimal?
0.5 or 0.05.
0.05, yeah. Okay, so filling everything in, this would be 30 times 1 minus 0.05
To the power of T.
to the power of T. What is 1 minus 0.05?
95.
95, 0.95 to the power of T. So my answer is A. Don't be fooled. Don't be fooled. Which of these were trying to fool you?
C. Because, wait, no. Yeah,
Yeah.
C, because that's the rate.
Yeah,
Of
C was
decay.
trying to fool you because that was telling you, oh, you forgot to add or subtract it from 1. And then D, how is D trying to fool you?
If you didn't like read the decrease, or you
Yeah.
didn't use the decay formula.
Yeah, for D, whoever chose D might have added instead of subtracted. All right. Try this one on your own. I'll put up a poll. We're almost done. Okay, while you guys are looking at the answers, I'll read. Population growth of a country is modeled by the function below, where T is time in years, based on the model, which is true about the country.
Miss, did you make it anonymous or?
Yeah, it's anonymous. take 10 more seconds. Pick your best answer. Three, two, one. Okay. Interesting. Okay, so B was the winner.
Wait, Miss, can I say something?
Yay.
Or like the answer?
Okay, what do you want to say?
You can automatically eliminate C and D because the A is going to be your starter, and the starter wasn't 100 million people; it was 10.
So
Miss,
10.
can I say something?
Mm-hmm.
I
What's up?
was gonna say that if you do the math and you do 10 to the power of 7, it's equal to 100 million. It's just a simplified version of saying 100 million because 100 million is a bunch of numbers. I did the math.
So here's a quick thing. I don't know if you had learned this before or not, but with an exponent, when you have 10 to the power of anything, that number tells you how many zeros to add. So 10 to the power of
That's
7
exactly what I did.
is 10 plus 7 zeros. 6, 7. So if I add in my commas, that's 10, that's 100 million. If you add 10 to the power of 4, for example, that's 10 plus 4 zeros. Once you add your commas, that's 100,000. So that's just something this isn't like an algebra thing, this is just a math thing. This is just general math facts, okay? When you do 10 to the power of anything, that's how many zeros you're adding to that number. So it was 100 million, not 10 million. So that was the first thing to notice. And then the growth rate, we know that this is 1.04. And what's 0.04 back to a percentage?
Wait, can you repeat that?
Okay, so inside the parentheses was 1.04. But what is 0.04 back to being a percentage?
Or percentile.
4.
Or, yeah, just 4. So for that reason, the answer is D, not B. B would have been correct if it was 10 million. So that was kind of a tricky thing to remember or to like figure out. But now that we know, we're not going to make that same mistake, okay?
Yeah, how many people chose D?
Oh, I don't know. I put away the answers. 2.
Carla and Jalen, good job.
Nice. All right. Couple more. The breakdown of a sample of a chemical compound is represented by the function P of t equals 300 times 0.5 to the power of t, where P of t represents the number of milligrams of the substance and t represents the time in years. In the function P of t, explain what 0.5 and 300 represent. So let's talk about it.
So 300 is A.
Right. So
And
300 is the A. And what does A represent?
the starting thing.
Mm-hmm. And what are we talking about here?
How much samples of chemical compound.
Good. So how the starting amount of the substance. And what units does it use here?
Milligrams.
Milligrams. Cool. So that's 300. That one's pretty easy. And then what about the 0.5? That should be 0.5. What does that tell me?
That how much
50.
how much more substance has been increasing? Or
So that's a good idea,
decaying?
but right. So that's the question. Am I increasing or decaying? Am I
Decaying because
growing or
it's the
decaying?
breakdown.
Okay. Right. It's breakdown. So that's a key word, breakdown. But just by looking at the number, how do you know that that's decaying?
Because it doesn't have a 1 in the beginning.
Yeah.
You can see that it was subtracted.
Right. Remember that in the general form, this would be 1 minus r. And if 1 minus r is 0.5, what is the value of r? Can you guys figure that out?
0.5.
Yeah, this would mean that r is 0.5. So by how much is this decreasing?
0.5.
50%.
50%. Yeah,
Oh, dang, that's a lot.
because 0.5
that.
is 50%. 50%. So it decreases by 50% every what? Each
Year.
what? Year. Good. Not too bad, right? Any questions on this one?
No.
Cool. I
Do we
think
have
this
Khan
was
Academy?
no. This is our last question. Wow, we
Oh,
got to
man.
everything, guys. We got to every single problem. That's awesome. All right, Tyrone, you want to
Awesome.
read our last one?
Yes. Wait, how do I pronounce that name?
Genevieve.
Genevieve deposited $400 into her bank account. The equation A of t equals 400 times 1.07 to the power of t can be used to calculate the value of her money after t years. What is the annual interest rate she is earning on her deposit?
So there it is again, interest. Remember?
Yes.
All right, so what is the interest rate?
The interest rate is
0.07.
Say that again, Perla?
Like without adding the 1, it's
Mhm.
0.07 or 70%.
Good.
Oh no,
So
never mind. 70%. My bad. Oops.
yeah. So 1.07 is 1 plus 0.07, which means that the rate R is 0.07, which is 7%.
70.
So the interest rate is 70%. 7%, I'm sorry. Now, this is a good type of interest because this isn't that she got a loan out, this is her putting money in a bank account. So you can also get interest when you put money in a bank account, but I've never in my life heard of such a good interest rate. Usually, like my bank account, my interest rate is like really, really low. It's like 2%. Because when you put money into a bank account, it grows, but it doesn't grow that much usually every year. So 7%, that's a really good rate. This girl better let me know where she's putting her money because I want to know. I want to put my money in there too.
Wait, is high interest rate bad or good?
It depends on the scenario. I mean, if it's a loan, it's bad because that's how much money you're owing. But if it's
Imagine
in a
having a
bank account, it's good.
50% interest rate for a loan.
Yeah, that would be ridiculous. All right, that is all. No more homework. But if you have any old assignments you haven't done, make sure you get those done.
No,
Y'all are
I
free to go.
wanted Khan Academy.
Bye.
Bye, miss.
Bye, guys.
Have a wonderful week. Wait, no week, because I see you tomorrow. Okay,
Yeah.
bye, miss.
Bye.